Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is the wind energy segment. We will discuss types of wind turbines, the physics of wind energy potential, where to place wind turbines, and the energy return on investment of wind turbines. Let's first discuss the basic designs of wind turbines. The horizontal axis turbine is the most popular design. In this type of wind turbines, the blades are shaped like airplane wings. As the wind passes through the wind turbine, the lift rotates the turbine while the drag is parasitic and tries to slow it down. So one of the design goals with wind turbines is typically to have them run at slow speeds but at maximum lift. That reduces the drag and we get the most energy conversion. This schematic shows the essential design features of a horizontal axis turbine. The propeller shaft is connected to a gearbox that increases the rotational speed suitable for the generator that is in the back. Then there is a yaw drive which adjusts the orientation of the propeller depending on the wind direction. The wind direction is measured with the wind vane that is at the back here. Furthermore, the blade pitch can be adjusted to control the rotational speed of the wind turbine depending on the wind conditions. The wind speed is measured with the anemometer that is also mounted at the back of the wind turbine. The yaw mechanism is also used to protect the wind turbine in case of too strong winds. When that occurs, the turbine essentially rotates 90 degrees out of the wind direction and the blades are adjusted as parallel as possible to the wind direction, which minimizes the lift and thereby the turbine suffers minimum torque on its structure. A competing wind turbine design is the vertical axis design. The advantages of this design are that they work with any wind direction because of their rotational symmetry. The mechanics are in the base for easy access, so one doesn't have to climb a tower. And there are lesser stresses on the tower since the structure can be stabilized with wires attached to the top. Now there are some severe disadvantages of this design, and this is probably the main reason why they are not used widely. They are not self-starting. One needs to use the generator or a motor to start the rotation. Furthermore, they cannot be turned out of the wind for protection because of that design symmetry. And there are high centrifugal forces in the wings because a lot of the mass of the wings is concentrated on the outside of the rotor. Furthermore, when the turbine rotates, the force on the wings is not constant during a full rotation because the angle of attack relative to the wind changes. And so this gives rise to an oscillatory force, and this can cause resonance phenomena. And so certain rotational speeds need to be avoided with this type of wind turbine. Let's focus at the basic physics of wind power. Wind turbines convert the kinetic energy of flowing air into electricity. And so we have a certain volume of air molecules that is moving through the turbine per time, and that is essentially the wind power that can be tapped. So if we want to calculate the power, we need first to calculate the energy, and then we can calculate the energy per time that goes through this cross section A. So the energy is just 1/2 times the mass of the air times the velocity of the air. And we can replace the mass of the air by density of the air times the volume of the air. So this gives us the energy in a certain volume of air. Now we can express this volume as the cylinder with the cross section A, and the length of the cylinder per time unit is just the velocity of the air times the time that we're measuring. With this we can rewrite this formula and express the volume of the air by multiplying the cross section times the velocity times the time. So we end up at 1/2 times the density times the area times the time times velocity cubed. So from this it's easy to calculate the power that goes through A, and that is then just this here, the kinetic energy divided by the time. and so we end up with 1/2 times the density times the area times velocity cubed. So you see, the power that can be extracted from a wind turbine must be proportional to the velocity cubed of the wind that is going through the turbine. Now, a cubic relationship, that means that the power increases very quickly with the velocity of the wind. And that immediately tells you that wind turbines are best placed in areas where the wind speeds are a little bit higher. It also suggests, we will see that in a bit, that wind turbines need to be placed in a certain distance to the surface of the Earth if one wants to optimize the power that can be extracted, because wind movements are typically faster at certain altitudes in comparison to the surface of the Earth, where there is friction with features that slow down the wind. An interesting question is how much of that kinetic energy in the air can be extracted. Since some of the kinetic energy of the air is being converted into electrical energy, the air has to slow down as it passes through the cross-section of the wind turbine. So the kinetic energy is less after passing through. What also happens is that the turbine swirls the air, and that results in a widening of the airflow. So we have a difference between the velocity of the air going in and the velocity of the air coming out of the wind turbine. So there's a law by Betz, and this Betz law predicts the power that can be extracted depending on the relationship between the airspeed before and after the wind turbine. Betz showed that the theoretical maximum of power extraction is reached when the velocity after the turbine is just 1/3 of the velocity of the air going into the turbine. When that is the case, then we can get almost 60% of the energy that is in the air. Since we need to have this ratio between air going in and out, this means that wind turbines need to be adjusted and optimized for a particular wind speed to maximize the energy conversion. Let's look at a real-world example. Here I show some data of the Vestas 3 megawatt turbine. Vestas is one of the largest wind turbine manufacturers. This wind turbine has a blade length of 66 meters. That gives it a cross-section of almost 10,000 square meters. Here is the power curve of this wind turbine. It follows the velocity cubed law up to a certain point, and then the output is constant. They do that on purpose by adjusting the blades of the turbine at high winds to prevent overload of the generator, which is designed for a certain average output power that is characteristic for the area where the wind turbine is deployed. So let's examine what happens at a wind speed of 10 meters per second. So the output power, the electrical output power, should be about 2.6 megawatts, 2,600 kilowatts. Now the wind power in the wind at this velocity, according to the formula that we just derived a couple slides ago, that is the density of the air times the cross-section times the wind speed cubed divided by 2. And so if you do the math, then you arrive at about 6 megawatts. So that's in the wind that goes through the turbine. The output is 2.6 megawatts. So if we divide the output by the input, we get a power coefficient of 0.43. If you remember, the theoretical maximum according to Betz is about 0.6. So that's the difference between theoretical maximum and what can be achieved under real conditions. Now we understand the power that can come out of a wind turbine. But what's really of interest is how much energy can we convert with it and translate into electricity. Here you see a graph that shows the seasonal wind speed in a place in Scotland, and this here is the months of half a year, and this is the wind speed in meters per second. So you see it goes from 0 to 30. So how does this now translate into energy output? We have here moments where there's very low wind speed, and then we have moments where the wind is blowing really hard. In fact, the red line, that is the daily averages of wind speed. So there are clearly windy days and less windy days. And the blue curve, this is half-hourly winds. And so you see that there is, on these daily averages, even in a day, we have a lot of variation that can be quite dramatic. This here can be statistically evaluated, and one can draw a wind speed histogram, which gives us the hours that we have a certain wind speed. And so things are now nicely organized, and we see that we have a certain maximum of wind speeds that is in a reasonable range for wind turbines. We also see that high winds only occur fairly rarely. So now we have the power curve like the one we saw on the previous slide. So first we have that velocity cubed increase, then the wind speeds at which they regulate the output power to be constant, and then at some point they even shut it down. And so if you multiply this power curve, which is energy per time, with the time we have certain wind speeds, we arrive at this energy output. So this here is kilowatt hours per wind speed, and the area under this curve, this is the energy output of the wind turbine. Obviously, it is an interesting question how many wind turbines one can place per area and not infringe with wind turbines that are in close proximity. Since the wind turbines slow down the wind and they disturb the flow in a wider area than their rotor diameter, we need to space the turbines in a certain distance from each other in order to prevent that we eat into the kinetic energy of adjacent and downstream turbines. And so it turns out that if we have a certain rotor diameter d, then 5d in either direction, laterally and downstream, is a good number to prevent too much of interference between the turbines. Another study came to a similar conclusion. There they found that a loss smaller than 20% can be achieved if there is a minimum of 7 rotors downstream distance and 4 rotors lateral distance. The bottom line is clearly that one cannot space them too closely, and that of course increases the area requirement if a certain level of energy conversion is desired. Another consideration for wind turbine placement is the height above ground. You see here an interesting experiment. They attached flares to the end of one of the blades. So as the wind turbine rotates in the wind, you see that the wind above here pushes the air faster forwards than the wind down here. And so this clearly shows us that the velocity at higher altitudes is higher than close to the ground. The reason for that is that there is friction between the airflow and surface features on the ground. The ratio between the velocity relative to a reference velocity at a lower height, that goes by the ratio between the heights to factor alpha, and alpha is 0.143. Now this suggests that the difference in speed is really not that much between down here and up here. However, since the power goes with velocity cubed, a significant power increase is observed if one puts the wind turbines at higher heights above the ground. This relation between power and height is put into real numbers in this table. And here you see, depending on the wind class from 1 to 7, the velocities and the wind power density depending on the height. And so we have 3 columns, 10 meters, 30 meters, and 50 meters. And if you compare between the 10 meters and the 50 meters, the power essentially doubles for all these wind classes. This immediately shows you that these small residential turbines that are attached to the roofs of houses or garages, they don't really have a lot going for them in terms of airflow power density. And also it is no surprise that most commercial big designs, they have high towers and they try to be in significant heights above the ground. So what's the potential in wind power to cover our power needs? Consider that 1% of the total solar power absorbed by the Earth is converted into wind, into kinetic energy of the atmosphere. That total sun power is 1.7 times 10 to the 17 watt. If that were distributed uniformly across the entire surface of the Earth, then on the landmass we would have about 3.4 times 10 to the 14 watt wind power. That compares with 14.3 times 10 to the 12 watt power need across the world. So that's a factor 25 approximately. When we just look at the US, it's a factor 100. Now when you compare these numbers, then you need to keep in mind that wind power is electrical and that the conversion factor is about 40% in a real life wind turbine, as we just saw. Issues are, of course, that wind power is not homogeneously distributed. There are vast areas where there is hardly ever strong wind, and then we have some areas where the wind is blowing fairly consistently. Of course, you want to put wind turbines in such areas. The US is one of the better wind places worldwide because we have a large area in the Midwest where there are high winds that are blowing fairly continuously. Here's a map of the global onshore wind power potential. The scale goes from 0 to 0.6 watt per square meter to 4.5 to 7.2 watts per square meter. You see that there are vast areas that are blue, so there is not much to do with wind power. There are also some white areas. These are areas that were deemed unsuitable for turbine placement. So these are the rainforests, permafrost, and also urban areas were excluded in this study. Overall, the wind power has a fairly low density. If you compare it with the insolation that is hitting the planet at 1000 watts per square meter, you see that there is this 1% factor very strongly evident. And keep in mind that the wind is stronger above the water. If you compare these numbers, these wind power numbers, with biofuels, you see that wind power has a much better potential per area than biofuels, which we just learned are very, very inefficient. So here we compare a number of 3 to 4 watt per square meter in the Midwest to 0.021 watt per square meter for biofuels. If you compare it with photovoltaics that run at 5% efficiency in a plant setting, there we get about 10 watt per square meter. So you see that wind plants, they will need about 3 or 4 times the area of a solar installation to produce the same output power. These maps show the feasible energy potential per country, onshore and offshore. So if we look at the US, we have 14 petawatt hours offshore potential, so if we put turbines along the coasts, and we have 74 petawatt hours onshore potential, so mainly if we put the turbines into the Midwest. So if you add them up, we have about 88 petawatt hours available of wind energy. This is about 3 times the energy needs of the US. We are currently at 29 petawatt hours. If you look at the world, that's about 125 petawatt hours. And so there are quite a few countries that have significant potential for wind power generation. So it appears entirely feasible that wind power could cover a significant portion of the world energy needs. So what's the wind power potential in the US? As I pointed out earlier, we have one of the largest high wind areas globally. Generally, areas that have more than 6.5 meters per second average wind speed at 80 meters height are considered suitable for wind power. So if you look at the color code of this wind speed map, then you see that all of these areas here that are orange to purple, they are good wind power areas. So what if we wanted to cover our currently used 33.6 terawatt hours per day energy need with wind power? So this corresponds to 1.4 terawatt output power, and we can use that number fairly directly because wind makes electricity, and so we don't have to compare this with the fossil fuel intake. It's more important how much output we need in energy for our use. So at a conversion factor of 0.4, the 4 watts per square meter that we may have per area of wind power density would require an area of 10 to the 12 square meter, and this corresponds to 1,000,000 square kilometers, which is an area of about 625 miles by 625 miles. I tried to sketch that in this map with this square, and so you see, in any realistic scenario we would have to use pretty much the entire area and plaster it with windmills if we wanted to consistently live off wind power. It's interesting to look at the distribution of the wind energy potential across the year. Here we have a graph that shows the onshore and offshore. So blue is onshore and red is offshore wind energy potential. So this is in terawatt hours, and note that the onshore potential is about a factor 10 larger than the offshore potential. Now the offshore potential scale, that doubles also for the consumption scale, which is in a similar magnitude. So what you see here is that in summer we have a dip in wind power, while in winter, in the winter months, wind power is strongest. This is reversed when it comes to the consumption because the need for air conditioning goes up. Note that the consumption is the electricity consumption in this graph. So in summer, because of the higher air conditioning needs, we have a spike in electricity need. So this here suggests that one could combine wind installations with photovoltaic installations, because in the summer months we have typically more sun available, and so one could compensate for that dip in wind power with a peak in solar power output. Now I want to discuss the energy balance of wind power, the energy return on investment. I found this interesting study by Kubiszewski where they performed a meta-analysis of 114 individual analyses of different types of wind turbines. Their boundary conditions included the construction phase, the operational lifetime, and the decommissioning phase. So here you see it on a timeline. If you look into the construction phase, then of course there's only energy costs. Once the wind turbine is operational, it outputs energy. So this is now this positive part. The blue part of it, that is the energy that is actually going into the grid. The orange part, that is the part of the energy that the wind turbine uses itself for its day-to-day operations. So what's going to the consumer is this blue part. After some years, the wind turbine reaches the end of its lifetime, and then we have to decommission it. So these are additional energy costs. So in the end, we have a net energy total that came out of the operation of this wind turbine, and we had some energy costs, and they, of course, together make up the energy that came out of the wind turbine. So the EROI is the ratio between the net energy output and the energy input. This graph is from the same study. It plots the energy return on investment depending on the power rating of wind turbines. So each of these data points comes from one of those studies that were investigated. On the left side we have small wind turbines, and on the right side we have larger wind turbines. And you see that there is a clear correlation between large EROI and large wind turbine size. Now this here ends at 800 kilowatt. This is considerably smaller than the currently built wind turbines of 3 or more megawatt. So one can assume that the current larger designs have an even better EROI. This graph clearly shows that larger turbines can easily achieve an EROI that is larger than 20. So we get 20 times more energy out than it costs to build and operate the wind turbine. The main reason for this relationship is that larger turbines access wind higher above the ground, which we know now has more power. This graph shows the wind power EROI in comparison to EROIs of other sustainable energy types. So you see that wind has a pretty good EROI in comparison to all the other technologies. In particular, if you compare to solar thermal, to photovoltaics, and to biofuels. Biofuels we know now are pretty close to 1 with their EROI, and solar energy is somewhere between 5 and 10. These values may be a little bit pessimistic. But there's no doubt that wind power has an EROI that is significantly higher than that of the other technologies. These graphs investigate the cost of wind power. The graph on top shows the development of wind-based electricity in cents per kilowatt hour from 1980 to 2012. And it's pretty clear that over 30 years the costs fell significantly. One can say that the cost fell by about a factor 5 in this period. At the same time, the number of installed wind turbines increased dramatically. There is now an installed capacity of 60 gigawatts in the United States, which is the equivalent of about 60 major power plants. The graph on the bottom that comes from the Fraunhofer Institute in Germany. It compares the levelized cost of electricity across various generation methods. And so we have here photovoltaics and wind, onshore and offshore, biogas, and then conventional fossil fuels. And so you see that onshore wind is the only sustainable technology that is comparable to the fossil fuel-based technologies. Before I summarize this segment, I want to discuss micro-generation wind turbines. They seem to have become popular in recent years because they are not too expensive. And so many people think one could significantly cut down on the power bill every month by having such a wind turbine. Now here we have an example, the Ampere 600. It has a rotor diameter of 1.7 meters. If you go to the website, a reference power of 723 watts is listed. Now, a glance at their power curve reveals that for this you need to have a wind of about 12 meters per second. So this is pretty unrealistic. We know now that high winds occur rarely, and that most of the time we have a wind that is much lower and much more gentle, especially if we are at a low altitude, like so close to this roof here. So what you can expect is that the wind will be much more in a 4 to 8 meters per second range if it's blowing, and so the power output will be much lower, probably between 80 and 400 watts or so. So that would translate, if you have constant wind that's blowing all the time, you would get 700 to 3,500 kilowatt hours. And indeed, they specify on their website that one can expect about 1,300 kilowatt hours from this turbine per year. This suggests that you need about 5 meters per second on average for this energy output to occur. And that is probably also a little bit optimistic because there are days without wind and at night wind blows rarely, etc. So if we assume maybe half of that as a realistic power output of this turbine, 650 kilowatt hours per year, and a service-free 20-year life, we can calculate based on the $3,000 that each kilowatt hour would be 23 cents. That is about twice as much than what you would pay to the local power plant. Now we assume service-free and no batteries and so forth, so the real cost would be probably considerably higher if you integrate this wind turbine into a control system. Now the average US home needs about 30 kilowatt hours per day, so you would need maybe 10 to 20 of such turbines plus batteries and so forth to really go self-sufficient with a house. So I think the bottom line for microgeneration wind turbines is that they are promising for off-grid applications, but if you're on-grid, it would make much more sense to install large wind farms and then generate power and sell it for a low price to the power customers. Summarizing, we can say the wind power potential in the US is about 3 times the current power needs. The EROI of wind power is probably the best of all the renewable technologies. It's about 15 to 20, probably better with current 3 megawatt designs. The price of wind turbines is now in the fossil fuel range. This comes mainly from installing ever bigger turbines. The energy density per area is low in wind, so that means that large parts of the US would have to be plastered with wind turbines. But we can conclude that wind power definitely has one of the best potentials to satisfy a significant part of the US energy needs. This concludes the wind energy segment. Thanks for watching.